Okay, so as we've seen and kind of done quite a bit of analysis based around a moving charge, right? For example, a current can induce a magnetic field. Not can, it does, right? It induces a magnetic field. So it's not surprising then that once this was kind of discovered accidentally by Ørsted, people started to wonder, can a changing magnetic field induce a current? Okay. And eventually it became apparent that it did. This was studied and eventually sort of proven and really nailed down by a scientist, a physicist named Michael Faraday. Though there were a few other physicists working on it, he gets the most credit usually because he kind of publishes results first. And so that's why this idea that a changing magnetic field, okay, it's important that it's changing, could induce a current. We'll get a little bit more to the mechanics of why that happens in the next topic. But Faraday's really the one that nailed down that it does happen, okay? So when a changing magnetic field is near something that would conduct, a current would be induced, right? Or induce, again, just a fancy word for produced. So a current is induced when a changing magnetic field is put near something that would allow current to flow. And so is this really that weird? Think about it. One of the main ways that we get electricity is with a battery, right? That is because charges want to leave the positive terminal and travel to the negative terminal, right? That's essentially what's going on in a battery is you put a bunch of charges that don't want to be near each other and allow them to move through a conductor. But in your life, is everything you use that is powered by electricity, does it all require a battery? Well, no, right? In fact, anything you plug in at home, there's no battery involved, okay? So can you have electricity without a battery? If the answer is yes, right, then we have to think about where it comes from, okay? And most of our electricity that we use in our homes comes from the fact that a moving magnet near a wire will induce a current in that wire. So we'll watch a quick video that just kind of goes through this discovery in a bit more depth, and then we will come back to this.
Electricity is one of those things we take for granted. We all know what to do with it. Plug this in, plug that in. Well, we're very good at plugging things in. But it takes a power failure to make us realize how utterly helpless we are without it. The basic principles that led to the development of electrical generators began with the discovery by Hans Christian Ørsted in 1819 that a magnetic field results whenever there's a flow of charge through a conductor. 10 years later, in 1830, the possibility that a magnetic field could generate a current in a conductor became a reality. Working independently, American physicist Joseph Henry and British scientist Michael Faraday performed similar experiments and arrived at the same conclusions. However, since Faraday published his results first, he is credited with the discovery of the effect which is now called electromagnetic induction. Faraday's experiment involved an iron ring and two coils of insulated wire. The primary coil is connected to a battery, and the secondary coil to a galvanometer. A galvanometer registers minute current flow through a conductor, with its needle also indicating the direction of the current flow. Faraday observed that the instant the primary coil was connected to the battery, the galvanometer registered a brief pulse of current in the secondary coil. But, much to his surprise, the needle quickly returned to zero, indicating that all current flow had stopped. However, when the primary coil was disconnected, current was again briefly generated in the secondary coil. Only this time the flow was in the opposite direction. Changing the current in the primary coil somehow induced a current in the secondary coil. Faraday recognized that connecting the primary coil to the battery causes a magnetic field to build up within the iron ring. As the field grows within the ring, it induces a current to flow through the secondary coil. Once the field in the ring is at full strength, it is no longer changing within the secondary coil. The result? No more current in the secondary coil. When the primary coil is disconnected, the magnetic field it produced collapses. As the field in the ring collapses, it again induces a current in the secondary coil, this time in the opposite direction. Faraday's apparatus would today be called a transformer. Experimenting further, he found that the same results were obtained using a bar magnet instead of the primary coil and ring apparatus. One of the most important conclusions from Faraday's experiments can be stated this way. As long as the magnetic field within the coil is changing, a current will be induced in that coil. This principle was used by French inventor Hippolyte Pixii in 1832 to develop the first electric generator. Although it was clear that induced current flowed in different directions, depending on whether a magnetic field was growing or collapsing, why it was doing this was a mystery.
Now, this idea that a changing magnetic field near a conductor can induce a current, think about it, it's kind of the opposite of what we call the motor effect. So the motor effect was that a moving current would produce a magnetic field, and then that magnetic field would interact with an external magnetic field to cause a magnetic force, which led to motion. Now we're going to have a moving magnetic field, and we're going to convert that into current. So the mechanical energy here is kind of going to be converted into electrical energy. It's kind of the backwards motor effect. This idea, this fact that the changing magnetic field can induce a current, this is known as the generator effect. So when do you use a generator? Use a generator when the power is out and you need electricity, right? So you fire up the generator. Usually generators run on gasoline or some other kind of fossil fuel, right? So why do they need the gasoline? Well, they take that energy, they turn it into motion to move a magnet and then to induce current to power whatever it is you need your generator to power, okay? So in general, the generator effect is taking mechanical energy and then converting it through the use of, well, what is going to move? A magnet is going to move, so the magnetic field will be changing, and so you will induce a current or electrical energy, the motion of charge. So let's think about what this looks like. So the generator effect. Did you know that pretty much any way you get energy just relies on this fact that a changing magnetic field causes current to flow? Okay, so here is one example, but this actually applies to every type of energy, including all renewables, right? And all non-renewable energy resources. So it all comes down to how do you make a magnetic field change? The most direct way to do that is to take a magnet and make it move. So this simulation is set up to show you how it works with hydropower, hydro being water power, right? But the exact same idea works with wind power. You get wind to move a magnet. Or in nuclear power, you use the nuclear energy produced to make a magnet move. Okay, the same goes for non-renewable sources of energy, such as burning fossil fuels. So when you burn coal, what do? You use the thermal energy that's produced to be converted into kinetic energy in a magnet, right, by turning turbines, and then you use that changing magnetic field to induce a current in a wire. So again, here's hydropower. So what do? You build up a bunch of potential energy by getting a bunch of water kind of high. You allow it to then be converted to chemical energy by allowing it to fall onto a turbine with a magnet attached. And then look what happens. So since we have, at this point here, we have a changing magnetic field. Again, we're going to get a bit into the direction next topic. For now, we're just focusing on the fact that a changing magnetic field will induce a current. Okay, but notice, because the magnetic field is changing here, and if you don't believe me that it's changing, we'll think about what's happening right now. Right now, the magnetic field is leaving north, going back to enter south. But now it's coming the other way. Now it's entering south, right? And we can actually see the field here. Look, notice how it is clearly changing. We can even put a compass there if we wanted. The magnetic field here is changing, and so a current is being induced. Notice it's going back and forth. This is what you might have heard of. So you know the band AC/DC. Do you know what AC and DC stand for? It's alternating current and direct current. So when you have like a battery, that is direct current because current always flows in one direction from one terminal to the other terminal. Direct current. AC stands for alternating current, in which current is kind of going back and forth. But either way, electrons are flowing through, and so electricity is being produced. Yes, there's a millisecond there where no electricity is flowing, but on the time scales that happens, it's almost imperceptible, okay? And so this is showing that, notice how it goes back and forth. That's because the current is going from flowing one way to the other way because of the changing magnetic field. And so when you at home turn on your lights, right, what is happening? Well, somewhere a magnetic field is changing that is causing current to flow through wires to your house, and there you go. Lights are being turned on, okay? Realistically, they're going on and off, but at a frequency that's so fast it's not even perceptible, right? But this is what's happening. Notice we have a changing magnetic field here, right? Changing magnetic field, which induces a current, which if you flow current through what you want to light up, it will light up. Okay, and just in case you're kind of looking at that going, all right, Maxwell, sure, you got a simulation that shows it, but that's essentially just a cartoon at the end of the day, right? It just helps us understand something. We haven't seen it ourselves, so how about I show you that an induced magnetic field can indeed produce a current? Again, we're going to get more into the why and the how in the next topic. For now, we're just focusing on the fact that a moving magnetic field will induce a current. Shouldn't seem that outlandish to you because we've already seen that a current, a moving charge, can induce a magnetic field, okay? What I have here is basically a coil with a bunch of wires, okay? It's a bunch of copper, so that is a good conductor. This thing here is called an ammeter, okay? Or when it's this small, it's often called a galvanometer. It measures very, very small amounts of current. So you can see the units that they have here are microamps. So the reason we have to go small is, well, this is obviously not a big, powerful setup, right? So if we do get current, it's going to be relatively small, okay? So if I have here the neodymium magnets. Those are fairly strong, okay? How do I make the current be generated? It's not going to be the big focus of today's topic, but one way I can change a magnetic field is to move the magnet itself. So I want you to watch the needle of the ammeter here. By the way, how does it work? It's just hooked up, okay? So you can see to one end of the conducting copper coil and then to the other end of the, runs through here. So if current is flowing, it will make the needle move. Okay, so just watch the needle. So I'm going to take this and I'm going to change it near the conducting coil. Notice that? So when it's going down, it goes that way, up the other way. But as soon as it stops, nothing, right? The magnetic field must be changing, okay? And to show you what I mean, I could also move the conductor towards the magnetic field because that's the same thing. That's still changing the magnetic field that's near the conductor. This kind of motion is actually going to be the focus of today's topic, but it's important to realize that it's not actually a different thing. It's just because for the conductor, the magnetic field is now changing. So again, the idea behind so much of our energy production is how can we make a magnet move long-term and sustainably-ish, right? So this is not one of our, we don't really have torsional energy. I don't think there's any, I don't think there's anybody that really generates their electricity by hooking a magnet up to a piece of string and twisting it. But if you watch the ammeter, okay, it is still a changing magnetic field near a conductor. And notice it's vibrating really quick because the magnetic field is actually changing really quick, but that still means every time it moves, there is current flowing through, right? That's pretty cool. So cool. So each time it reverses, the direction of current is reversing. So current's going, and if I had a light bulb hooked up to this, it would be lighting up, or at least current's being produced, right? It would depend on how much current is required to actually light up the bulb, but either way, electricity would be flowing through it. It might not get very bright depending on how much current needs to be flowing through it. Okay, so there are three ways to change a magnetic field so that you can induce current, okay? Three big ways anyway. So we could change the magnitude of the field, make it larger, make it smaller, make it larger, make it smaller, perhaps this is an induced magnetic field and we are changing the current. So the magnetic field that we're going to change by inducing it stronger or weaker with the original current, okay? We could move the field. That's what you saw in that simulation, right? I.e., to move the field, what do? You move the magnet, right? That's how most of our energy works. Make a magnet move and you can induce current, and that means you can produce electricity, okay? Or there's a third way that we are going to look at right now. That is to move the conductor. Now, when you move the conductor, okay, now, when you move the conductor, you might be saying, hang on, you're not changing the magnetic field, but you are from the perspective of the conductor, right? You are changing the magnetic field that the conductor is susceptible to. So to go back to the simulation for a second, notice, look, okay, see how the field everywhere? If I move this through the field, then I'm changing the magnetic field that the wire is exposed to. So I could do this, move the magnet. You'd have no problem with saying that's a changing magnetic field, right? Well, what's the difference between doing this, right? Motion is kind of relative anyway. So you could say here, the magnet is moving towards the coil, or you could say the coil is moving towards the magnet, same with the way. So it's really, right, motion is kind of relative. So moving the conductor produces the same result as moving the magnet, because either way, you are changing the magnetic field near the conductor, right? So this is going to lead to kind of one final application of our third hand rule. What if you move the conductor, okay, within a magnetic field? How will that change the current flowing through the conductor? Or how will it cause current to flow through the conductor? We call it the third hand rule, part B, but honestly, there's nothing different about the regular third hand rule. The only difference is that now that magnetic force that's going to act, okay, is going to act on the charge to cause it to flow in the first place, instead of it already having flowed, and then the force is going to act kind of externally. Now, the force is what's actually going to cause the charge to flow, okay? So the third hand rule, part B, you might want to call it, but even though it's really not that different, for an induced current created by a moving conductor, and I should say, like all third hand rules, within an external magnetic field. So you'll see what I mean. Nothing new here. Your fingers point in the direction of the magnetic field. That is no different than our third hand rule, quote unquote, part A. Okay. Now your thumb points in the direction of the moving conductor. In the first kind of part of our third hand rule, what did your thumb move in the direction of? It moved in the direction of the moving charge. Remember, where are those charges? They're in the conductor. So not much is actually happening different here. You're still going to move the charge. You're just going to now see, okay, what force would it feel, and so which direction would it flow? So your palm then shows the direction of the induced current, right? But your palm is still showing the magnetic force, okay? It's just now that that magnetic force is going to be what pushes the charges through the wire. So sure, it does show the direction of the induced current, but it's because Fm is going to, the magnetic force is going to push the charges through the wire. So this is honestly not a different hand rule, okay? It is still the same thing as the regular old third hand rule. It's just that now we think about it a bit differently because current was not already flowing. We're going to move the charges within the field, but then that motion is going to cause a force, which is now going to cause them to move through the conductor. So maybe you'll see what I mean when we do a few examples, okay? And again, your thumb points in the direction of the moving conductor, but this is still the direction of charge motion, because where are the charges? They are in the conductor. So no, it's not the way they're going to end up going in the end. But remember, we've never said that. We've always just said what's the initial force they're going to feel. Okay, so we're still saying they move this way. What force do they feel? And then if they feel that force, what direction do they flow through the conductor? Okay, so I'm going to take this to some paper so I can film myself actually doing the hand rule, because it doesn't help you out much if I just talk about it. Okay, so kind of like I said, right, there is not actually that much difference there is actually nothing different in terms of physics concepts here, although we do have to be a little bit more careful with how we apply it. This is the same old third hand rule. It's just we're going to think about what that magnetic force is causing, maybe a little bit different than we would have before. So we have here, okay, the question asks, which way will conventional current flow? So conventional current, of course, conventional current, it's basically saying which direction will conventional current flow. Okay, so which hand should we use for conventional current? Again, that's never changed. That'll be our right hand, right? Because conventional current is what a positive charge would do. Okay, so right hand is for positive charges. Okay, so our fingers point in the direction of the magnetic field. Well, how does a magnetic field look? It goes, leaves north, enters south, right? Leaves north, enters south. Okay, there we go. So that's what the magnetic field looks like. It's kind of going all around this wire. Now, our thumb points, yes, in the direction of the moving conductor, but remember, there's charges in there. So that's why the magnetic force is going to exist. When we push this moving conductor down, when we take it and apply that force down and make it move, all the billions and billions of electrons that are in there are now moving. And so they're a moving charge in an external magnetic field. And all we're doing is saying, hey, what force would they feel? Once we know what force they would feel, we know which way they're going to flow because of that motion, right? Because of that change in the magnetic field. So notice that our magnetic field is that way, right? We are going to cause the charges to move that way. So yes, they are perpendicular, so there will be a magnetic force. Which way can it be? Remember, it's going to be perpendicular as well to those two, right? So our only option is either out of the page or into the page, right? Or I guess along the wire or out of the wire, okay? So let's take a look. If I use my right hand, I'm a charge, I get pushed down. Yes, I'm in a conductor, but I'm still getting pushed down. Okay, magnetic field should go that way. And if I'm a charge, I get pushed down. So what force pushes me along? Well, there's clearly a force pushing me. I'm not following the hand rule now. I'm just saying, okay, there's a force in the wire pushing me as a positive charge, a part of the current, forward, out. Think of it like a tube of toothpaste, right? The force is squeezing the toothpaste, the current, out towards this way. So if I'm a positive charge, I'm going to get pushed by the force this way, okay? Now, this also explains why the magnetic field needs to be changing, otherwise there's no current, right? So if, remember, by moving the conductor, I'm causing a change in the magnetic field because it's moving through a different part of the magnetic field, right? And so if I stop moving it, what happens to the V of the charge? Because remember, the magnetic force equals QVB, right? So this magnetic force that is causing the current to be produced is going to go away if I stop moving either the magnetic field or the conductor, right? So by moving the charge through the magnetic field, I am causing a magnetic force to be produced that's going to end up, pushing this current towards me. So the conventional current would be out of the page, right? So again, the wire was moved down, so the charges were moved down, so our thumb goes down, and then what do they feel? What's the next force they feel? They feel pushed, and so the charges move along this way. And again, so why is the current that way towards us? Because the magnetic force is that way towards us. So not actually that different from what we've been doing with our third hand rule so far. Okay, example 2, a conducting rod is placed on a U-shaped wire and is moved as indicated. What is the direction of the induced electron flow? Okay, so here's our magnetic field over here, right? Tell it's into the page. Those are arrow tails, so our magnetic field into the page here. Now we're going to take this conductor and is asked about induced electron flow, so this will be negative. We'll use our left-hand rule, okay? So now it's saying if you take a whole bunch of electrons that are not flowing right now, but they're in there, and you move them this way. Well, that's still moving electrons, right? That's still taking electrons and making them move because they are in the wire, right? So if we take these electrons, make them move, now what force are they going to feel that's going to squeeze them either that way or squeeze them down that way through the tube, cause current to flow, or I guess electrons to flow in this case, okay? So electron flow. This is going to be our left hand rule. So let's take our left hand. We're going to point our thumb in the direction that we're going to make those move first, right? The conductor is going to get pushed that way, which means all the electrons in there are going to get pushed that way. We have a magnetic field into the page. And so when we cause that motion, what force are they going to feel? If we make them move that way and the magnetic field is into the page, electrons are going to feel a push down towards the bottom of the page. So electrons are going to flow this way, and then they're going to go through that force is kind of going to carry them through, right? Carry them through the conductor, and that will be the direction of motion. So viewed from this way, we could say that the wires will flow through the conductor in a clockwise motion, right? Clockwise from our point of view. Or initially, what is the direction initially? It'd be towards the bottom of the page. Notice, what's a good clue that this is going to be induced electron flow? Well, that's an ammeter, okay, not a power source. There's no battery here. So the only way to get electrons to flow is by inducing the current with a magnetic field, right? Notice as soon as we stop, Fm equals QVB. So there's no V anymore for the electrons if we stop them, right? And therefore there will be no magnetic force causing them to flow, right? We could make it go back and forth by going like this, right? Then the electrons would go that way, that way, that way, that way, that way, that way, because the force would be going from bottom of the page, top of the page, bottom of the page, top of the page, bottom of the page, top of the page, bottom of the page, top of the page. Okay, so I just want to be clear, why are electrons flowing this way? Well, because the magnetic force is also that way. Okay, I like this one. So one diagram, two totally different questions that you might be asked, okay? So the first is, what direction would the wire jump? Okay, what is that asking about? Well, it's saying, will the wire jump? So that would imply that this electron flow was already here, and that's going to cause a magnetic force to act on the wire itself and make it move. So again, this is kind of driving home the point of be careful. Was the current induced or not, right? So in this one, with the direction will the wire jump? That would mean the current was not induced, right? Not induced. Because it's jumping, not because we applied a force, but because some magnetic force has been applied on it because of the flow of electrons. Right? Electron flow leading to a force, if that's the wording of the question. Whereas in this one, what direction was the wire moving? Okay, now a force, a movement in the wire led to electron flow. So induced. Okay, let's answer A as if this was not an induced current. So it's an electrons, they are moving kind of this way. We can think of that as out of the page for all intents and purposes. Which way is the magnetic field? Enter, exits north, enter south, exits north, enter south. Again, electron flow is that way. So for the third hand rule, okay, we will take our left thumb, point it out of the page, fingers go along the magnetic field line, and it looks like this wire will jump down because why? The magnetic force will be down. So magnetic force down for A. So towards bottom of page, I should say, not down. Okay, but now let's look at B. What direction was the wire moving? So it's saying if the wire was moving and this current got induced, which way must it have been moved? Well, let's think about that. So the magnetic force, which way, I want you to ask yourself right now, which way would the resulting magnetic force have had to be to make electrons do this? Well, it would have to be like a tube of toothpaste squeezing those electrons from the back to the front, right? So the magnetic field would essentially, the magnetic force would essentially be out of the page. Magnetic field's not going to change. That external magnetic field's still going to look like that. So which way would this wire have had to have been moved to induce this electron flow? Well, which way is your thumb pointing, right? Which way would the charges have to been moved to induce that force to cause them to then feel a force along the wire? They would have had to be moved up, right? So for B, the wire would have had to be moved up. Okay, so two completely separate questions. The electron flow and the magnetic field hasn't changed here. In one, the electrons were already flowing and the magnetic force resulted from that. In the other, the electrons are made to move and then a magnetic force caused them to flow. So in B, what direction was the wire moving? Toward top of page. So don't forget where we've come from. Yes, today we've now kind of put together that when a conductor experiences a changing magnetic field, a current is induced. But what do we know that a current induces? What did we just spend a lot of last topic talking about? We talked about an induced current creates its own magnetic field, right? A current induces a magnetic field. So a magnetic field induces a current, which induces its own magnetic field. There are now two magnetic fields. Okay, the original one, the external one, we would say, and a new induced field. So how can that look? Okay, example 4. What is the direction of the induced electron flow? What is the direction of the induced electron flow? So electron flow, which hand? Left hand, okay. And remember, yes, this always means the direction of the motion of charge. This is the initial direction of the motion of charge, right? In our other one, the force was going to change the motion anyway, so this shouldn't be that weird to you now, right? We were just looking at what's the initial kind of force that will be felt based on the initial motion of the charge. So all those charges in that wire, the electrons are going to be moved that way at first. Now the magnetic field here, this time is a bunch of dots. So dots towards you, right? Magnetic field is toward us, moving that way. So the electrons are going to be pushed that way through the wire. Okay, so the electrons are going to be pushed that way through the wire. From this perspective, that means they will flow, what is that, counterclockwise. From our perspective up here, looking down on it. Okay, so there we go. That's the induced direct electron flow. What is the direction of the induced magnetic field? Aha, okay. So what do we know? A changing magnetic field induces a current, right? But hey, what does a current induce? A magnetic field, right? A changing magnetic field induces a current, but a current induces a magnetic field. So if this wasn't here, if you hadn't learned any of this, last week I would have showed you this and said, hey, it's a moving charge. What does it induce? You would have said a magnetic field. Guess what? How that charge got moving doesn't change whether or not it induces a magnetic field. So this is a moving electron. It's a moving charge. It's going to induce a magnetic field. So what's it going to look like? Well, which hand rule helps us here? We have, is this a curly current or a straight current? Well, I guess you could kind of say it's both, right? So if we could kind of use our first or our second hand rule, it's going to work for us fine either way. So for a straight current, we would take our left hand, thumb is the direction that a negative charge would move. Okay, over here, which direction is the induced field? Well, it's out of the page, right? Okay, but on this side of the wire, which way is it? Well, it's into the page. Okay, same thing up here, into the page. Same thing down here, into the page, and here, into the page. So everywhere inside the loop, it's into the page. Everywhere outside the loop, if you want to check, out of the page. Okay, and what would I mean? What did I mean by you could kind of use either hand rule here? Well, remember, since this is kind of like a circular current, take your left hand and look. Everywhere inside, right, it's going into the page. So it does actually kind of work there. Okay, and then those magnetic field lines would go down, loop around, and then you'd get a north. So what is the direction of the induced magnetic field? Well, we'll say into the page, inside the loop. What is the direction of the induced electron flow? Counterclockwise, around. Okay. An external magnetic field into the page. Not a proper sentence. An oxygen nucleus enters the field from the right. Sketch the situation. So first things first, an external magnetic field into the page. So an external magnetic field into the page. Those are going to be, they're going away from us. They're like the tail feathers on an arrow. So that's a bunch of X's. Okay, it enters from the right. Whoops, should have given myself more room. It enters from the right. Sketch the situation. So we have an oxygen nucleus. Okay, what is an oxygen nucleus? Well, it's an oxygen atom and take away all its negative electrons, right? All of the electrons orbit the nucleus. We'll get to why that's a sketchy statement, but the electrons are around the nucleus, okay? And what's in the nucleus? A bunch of protons and neutrons. So the nucleus is definitely positive. How positive? Well, if you look on your periodic table, and yes, you will get a periodic table in Physics 30, okay? It is atomic number is 8, so it has 8 protons. So this, what does an oxygen nucleus look like? It's O8+. Okay. Now it enters the field from the right. So right or left hand rule. This is going to be our right hand rule. Okay, so we'll take our right hand rule, and it's going to, here's the direction of motion. Okay, it's going to come in like this. The magnetic field is into the page. Okay, so what kind of force does it feel? Well, it feels at first towards the bottom of the page, but as we know, right, then it's going to, right, as that direction of motion changes, so too does the direction of the magnetic force, so that it ends up being a center seeking, a centripetal force, right, and we end up with circular motion. Okay, so I just drew it again because I drew in all the FMs and realized, whoops, I didn't leave room for the new part. Okay, so great, that's the direction of the nucleus path. A, done, boom, that's old stuff. What's the direction of the induced magnetic field? Okay, so it's not this guy, that's the external magnetic field. That's not being induced. What magnetic field is going to be induced here? So what induces a magnetic field? Well, a moving charge induces a magnetic field. So here's our moving charge. Okay, let's take a look at it. Where it's going to be strongest anyway, inside, okay, within the loop. If we take our right hand rule, look at that. Okay, so inside the loop, it's always out of the page. Always out of the page in here, right? Or if you want, you can even do, it actually makes more sense to use the second hand rule because this is a circular charge motion, right? But you get the same result either way. your thumb points towards north along the field line, so north. Your thumb points towards the North Pole, right? So this is the North Pole is somewhere up here. The South Pole is somewhere below down here. Okay, so you may be thinking to yourself, why are we going back to this stuff? This doesn't really seem to match with the stuff we were just doing about a moving conductor. And you're right, kind of, okay, but it is to get us to the next question where we're just kind of thinking about, hey, okay, so we had an external magnetic field into the page, and then the induced magnetic field by the moving charge was out of the page, right? So a field caused motion in a charge, which induced a magnetic field, but that magnetic field was opposite to the external. So this idea of the direction of the magnetic field induced by the current, which was itself induced by a change in the original magnetic field, right, is going to become extra important tomorrow. It's going to really kind of bring some clarity to tomorrow's topic, which is just a general look at current induced by a change in a magnetic field, right? A change in the motion of charge caused by the change in a magnetic field. And then tomorrow for our last topic of not only chapter 12, but this whole electricity and magnetism unit, we'll just wrap up some of the kind of the nuts and the bolts of how and why the direction of the induced current depends on the change in the magnetic field that caused it, and then also sort of its induced magnetic field. But for now, if you're wanting some practice with this initial stuff, try the first one, part A, page 620, number 1, the first question on the 12.4 assignment.